Hello everyone, this is the fifth video of this series, and in this video we are going to discuss oscillator circuit. So let's make the Wein bridge oscillator. Wein bridge oscillator. So we all know the Wein bridge oscillator circuit, and this is a audio frequency oscillator. So its frequency should be less than 20 kilohertz. So let's design this circuit. So I have already calculated the values. So I will take R equal to 10 kilo ohm and C equal to 10 nanofarad. This will give us frequency equal to 1.59 kilohertz, which is approximately 1.6 kilohertz, and the time period will be 0.628 millisecond. So let's make this circuit and see what happens. So I have to start schematic. So first of all I have to take the op amp, right? So I search op amp, search. So remember, in this search panel, if you just click basic, normally you only see this one. Okay, so if you click this advanced, then only this description search menu comes, because if this description search is not available, then you have to type the exact part number. Like in our op amp we have to write mu A741. So I have to exactly type this. But if you have this description search, then you can search op amp and you will find this mu A741, because this is the commonly used op amp for analog applications. So I will take this. Place and close. So I click this. Slightly zoom. Okay. So this is the op amp we have. Now this is an op amp, so I must have the biasing circuit VDC. So I need two voltage sources. This is 12 volt and this is also 12 volt. So what I do here, I connect them. So if we can use a wire, or we can directly drag this connect and again drag it. It's done. So I need the ground. So I draw a wire. Okay. So I connect this plus VCC. So you can press Ctrl W. I can connect this plus VCC with pin number 7 and the minus 12 volt to pin number 4. So our biasing is done. Now we will need resistors for the feedback network, because the amplifier part, let's name is R1 and this is RF. So I connect them. This will go to pin number 6 and I need the ground. Again I have to connect this with pin number 2. So this is the feedback part, or the negative feedback part. So this makes the amplifier. Now we have to make the positive feedback network. So as we know, because if you don't know the theory of Wein bridge oscillator, I request you to go through the theory part first. I am not going to cover the theory. So here basically there is a series RC network and a parallel RC network. So I make them. Then C for capacitor. So I type Ctrl R to rotate it. Ctrl R means rotation. Then I have to connect them. So again I Ctrl W to make the wire. So connect this with pin number 6. This with this. Again I have to make them parallel. And I connect these two, and this will go to here. So it is connected, and this will be just connected to ground. Okay. So with this our circuit is connected. So this is the Wein bridge oscillator. So we calculated the values. Our resistance was 10 kilo ohm 10 kilo ohm, and this was 10 nanofarad. 10 nanofarad. This will also be 10 nanofarad because this RC should be same. One is parallel and one is series, and this is 10K. So just for if you want to take a printout or a screenshot, you can arrange these values. So let us drag it here. You can drag it here. So now it looks cleaner. Okay. So now let's okay. So before we do the simulation, we have to set up and see for this because we have seen two types of analysis. One is AC sweep and one is transient. And for this particular case, this is an oscillator. So we have to look at the waveform. So we must give a transient analysis. So now our time period is 0.628 millisecond. So so let's make it 4 millisecond so that we can see some 5 to 6 waves. Okay. Again, we know that the gain of the amplifier should be greater than or equal to 3. Once again, I tell you, if you have not gone through the theory, you can always go to the theory first. There are many materials online. Let me show you one good example. If I search Wein bridge oscillator, then this electronictutorials.ws. So this is a very good website, and here the working of this circuit is very nicely explained. So you can go through this website if you want to study the theory and how the circuit works. Okay, so let's come back. So the gain should be less than or equal to greater than or equal to 3 to meet the Barkhausen's criteria. Currently the gain is 1 plus RF by R1. This is we are applying the input to the non-inverting terminal. So this is a non-inverting amplifier. So the gain is 1 plus RF by R1, which is equal to 2. But our gain should be greater than or equal to 3. So let's make it 2 kilo ohm. So now it is 3K. The gain is 3. Okay, so let's now run the simulation. I have to save it first. Let's make a so this is a good habit to keep everything in the same folder, in a separate folder, because whenever you make in a separate folder, it is easy to find out. So let me make a folder for this Wein bridge. Let's make it suppose WB Wein bridge. Okay, so our simulation is done. Let's see what happens. Okay, I have done one mistake. I have to put a load resistance because I have to see the voltage across the load resistance. Okay, so let's give the load resistance one more resistance. Again, I give controller. Now see what in the last class, in the last video, I said that the terminal 1 and terminal 2. So you can see here, when I press Control R, it rotates in such a way. Now this terminal becomes terminal 1 and the upper terminal is terminal 2. So when I connect this one is terminal 2 and this one is terminal 1. Let me name it RL, and this should be connected to ground. So you can draw a wire from here to here, or you can put a separate ground, because if we put a separate ground, it looks nice. Okay, so now let's now run the simulation. So this is the terminal 2 of RL. So I have to see the voltage at this point. That means RL is to 2. So let me make, because I want to plot the voltage, this is RL is to 2. Okay, nothing is coming. So why it is happening? Now see, oscillator circuit is not so easy, right? Oscillator circuit is slightly complex compared to other circuits. Now see, here it is a 10 kilo ohm, right? 10 kilo ohm. If you look only at the resistor part, this is 10 kilo ohm, and this capacitor will also have some capacitive reactance, and this is a very low resistance part. So the feedback, most of the feedback current will flow this part. If we plot the current, you can see if we plot the current across R3 and current across RF, if we just compare, This is why I say that for analyzing circuits like an oscillator, it is always like more convenient to use an simulator compared to a, sorry, this is not RL, compared to a hardware. I want to see the current across I3, R3 and RF. So you can see this is R3, very high current, RF almost zero current. So since this value is very, very small, so what happens, most of the current goes through here. Most of the current goes to RF, because RF is red, most of the current goes to RF. So by maintaining the ratio, if I increase this value, let's make it 20K and let's make it 10K say. Okay, so I make this 20K and 10K. Now these two are almost equal, we can say. So now if I run the simulation again, let's see what happens. So this time if I again see IR3 and IRF, again there is a huge difference, but this is in nano ampere, you can see. So the difference is not so large. Let me plot the voltage and we will see what happens. So delete all traces, add trace. I want to see the voltage across RL is to 2, and I click this. Okay, we are getting something, but again this is not so cool, right? So what is the problem here? We can see that this RL is very small, so a large amount of current is directly going to ground maybe. So let me slightly increase this. Let me make it 10K. Okay, now I want to see the voltage across RL is to 2. Still nothing is coming. So what can be the problem? Let's make it 30K. RL is to 2 I have to plot. Okay, now something is coming, but what is coming? You see, it is in the millivolts range actually. You see, it is building up, because see, normally when we see the waveform just in a CRO, we don't see this transition period. It takes some time to develop, because we know that after the loop runs for a few number of times, then only it gives some stable input, and this is where the damping factor and all these parameters come into effect. So what we can do here, we cannot say anything, right? So one thing we can do is we can increase the time. So instead of 4 milliseconds, let me make it 10 milliseconds and see what happens. So now it is 10 milliseconds. So we have a few more number of cycles. Okay, see, now it is happening, right? See, this is 20 volt, so it is clipping off actually. Our gain is more, because I gave this gain as 30K. Let's make it 20K. And one more thing we can do, here we have an option, in the transient we have one option, skip initial transient solution. So if I click this skip initial transient solution, then we can actually skip the transient part to some extent. Yes, I want to see the voltage. VRL is to 2. Okay, so now it looks good, right? It looks good. Let me see the time period. Okay, so let me just make it 4, just to make it easier to compute. Let me just make it 4. So if I make it 4 milliseconds, there should be around 6 cycles. Okay, so 1, 2, 3, 4, 5, 6 cycles. So because our time period was 0.628 millisecond, So 6 into 6 is 36, so 3.6, so slightly almost equal to, because it is not exactly accurate, but we can get something. But again, this is in millivolt range. If we want to slightly increase this, what we can do is we can slightly reduce this 10K. Let's slightly reduce this, let's make it 8K and see what happens. So we will see this voltage IRL is to 2. Okay, again it is taking some time, but now it is building up. But is it clipping? Yes, definitely it is clipping. So the adjusting this is important. So if I make it 9, okay, I am getting slightly better result, but again it is in millivolt range, but slightly it is increasing. So if I make it, if I simulate it for some longer period of time, let's make it again 10 millisecond. And we see it is increasing slowly, but again it is becoming unstable actually, because the gain is more than 3. So it is difficult to get a good solution in this particular circuit, but still we can handle this. So this is how we can actually see a simulator, see a oscillator in a simulator. But so it is always a good practice to use either here or here. You can use a pot, but unfortunately pot is not available in this particular software. This particular software does not provide a potentiometer or dynamic solution, so we cannot have this. But if you use something like multisim, you can get a pot and you can adjust this and see the result. But for now I think this is good enough, because you can see all the parameters. If you want to see the current, then also there are options. You can even yourself you can study the current through all these resistors and capacitors and see what happens, how it actually works. So with this I want to complete this lecture. Thank you.